So hybridization is this thing. Like we did study that what happens to orbitals when they bond, right? I mean, the orbitals kind of change when they bond. Like if you look at a spherical s orbital, the electron over here, the electron is over here in this area over here. What happens is that when the bonding happens, the orbital changes shape. The same applies to this one. When the two orbitals mix up, the electrons, they get attracted and they get stuck in the middle. The orbital changes shape. The bonding orbital changes shape. So hybridization is nothing. It's a change of the shape of the orbital when an atom goes when an atom decides to bond with another atom. The orbitals are going to get stretched. The electrons are going to get pulled in different directions, which is why the orbital kind of changes shape. So the technical definition for this is it's the mixing of orbitals to form new hybrid orbitals. So it's the mixing of orbitals to form new hybrid orbitals. And I'm going to explain. So, and the simple meaning is, which is not the definition, but like a simpler way to understand this is, it's orbitals changing shape when they bond because the electrons get attracted by another atom. So we're going to focus on carbon's hybridization. So we're going to focus on carbon's hybridization. And carbon has three types of hybridization. The first one is Sp3 hybridization. Now, what is Sp3 hybridization and when does this happen? That's the first one. And let me explain this. Sp3 hybridization for a carbon atom will happen usually when carbon is forming only sigma bonds. It forms 4 sigma bonds, or we can, in other words, say a sigma bond is a single bond. So it forms 4 single bonds. So it forms 4 single bonds. And the shape of this carbon would be tetrahedral. And the angles would be 120 degrees, not 120 degrees, 109.5 degrees. So it's going to be 109.5 degrees. These are all the properties of what Sp3 hybridization is. We still don't know what Sp3 hybridization really is. Now, the first thing about hybridization, let's focus on carbon's electronic configuration. It's got 6 electrons. I mean, right now, I've just stated this, and we're going to explain or understand all of this. So carbon has 6 electrons. So the electronic configuration is 1s2, and it's 2s2, and 2p X, 2py, and 2pz. And this will have 1, this will have 1, and this one would be empty. So this is carbon's outer shell. It's got 4 electrons in total. So there are 4 electrons in the outer shell of carbon, and they're distributed in this way. Now, the first thing that is going to, I mean, remember, ignore the inner shell because that's not going to be involved in bonding. So I don't care about this one. These are the outer electrons. It has 4 shells, 4 orbitals, and total of 4 electrons. It can gain how many electrons? Like if carbon starts pulling electrons from other atoms, it can gain 1, 2, and 2 over here. So that's a total of 4 electrons. So it can gain 4 electrons. The first thing that happens is atoms distribute the electrons in the outer shell to maximize bond formation. Electrons in outer shell to maximize bond formation. What I mean by that is, imagine carbon at the moment. Like you've got a carbon atom and you have the orbitals in front of you. So imagine carbon over here. Carbon at the moment has 2 electrons in the 2s. So that means 2 electrons are together. So, I mean, in a simplistic way, these are the 2 electrons that are together, right? There's 1 electron in one orbital, there's another electron in the other orbital, and there's one empty space available. So there is one space. I'm going to put a square over there. So there's one space on one side that's completely empty. The 2pz is empty. The z-axis is completely empty. There are no electrons, right? Now imagine 4 hydrogen atoms coming in. So this is one hydrogen atom. There's another hydrogen atom. Here's a third hydrogen atom, and here's a 4th hydrogen atom. Now, each of the hydrogen atoms, they need electrons. They need exactly 1 electron. So they all need electrons. And they see carbon's 4 electrons. So there are 4 electrons over here. And they see those electrons, and they're going to try and attract those electrons. So what will happen is, this hydrogen is going to try and pull 1 electron. This hydrogen is also going to try and pull 1 electron. This hydrogen is also going to try and pull 1 electron from carbon. And this electron from carbon. And this hydrogen over here at the bottom is also going to try and pull 1 electron towards itself. So it's going to try and form 4 bonds, 4 sigma bonds, because the first bond is always a sigma bond. So the hydrogen atoms, they see carbon's 4 electron, and they're going to try and pull each of the electrons towards themselves, right? Is this point clear so far? Is this clear, Munib? Rima, is this clear? Hamza?
Yes.
Yes.
Now the thing is, do you think these 2 electrons would be together, like if they're bonding, or would they be in separate spaces? I mean, when they bond, 1 electron is getting pulled over here, and the other electron is getting pulled by the other hydrogen atom. Is that clear? I mean, is this point clear that the 2 electrons are not going to be together? Is that clear?
Yes.
Yes.
So this is the idea that an atom distributes its electrons to maximize bond formation. So what will happen is, the 2 electrons are going to be pulled, and this empty space over here, it's going to be utilized. Like, why keep that space empty? Like, carbon will distribute the electrons all around it, so that the hydrogen atoms can sort of bond with each one independently. So the electrons would exist in separate regions. Separate regions meaning separate orbitals, right? So this is what will happen. The 2s is not going to have 2 electrons when it's bonding. Instead, the 2s will have just 1 electron, and one of the electrons will be sent to this empty space over here, so that the electrons kind of get distributed now. So they're all in independent orbitals now. One orbital get bonding with this one over here, one over here, one over here. So that is what I mean by atoms distributing the electrons. That's what's going to happen. That carbon, instead of it being 2s2 and 2px1, 2py1, and 2pz0, it's actually the electrons are all going to get distributed in all the orbitals evenly. Is that clear? Is this point clear?
Yes.
Yes.
And also remember that for distribution to happen, you need empty spaces, right? Like this electron, there was an empty space over here. So this electron decided to come to that empty space. If there are no empty orbitals available, distribution will not be possible. So keep that in mind as well. So atoms can only distribute the electrons if they in the outer shell there are empty spaces available. So only if empty orbitals are available. Just a second, the board is hanging. So only, let me go back. So remember this thing. Just remember this point that atoms are always going to distribute the electrons evenly. So I'm just going to stress on that point further. So in this way, a lot of atoms can maximize bond formation. They can have, they can form multiple types of bonds. So one example, like I'm just going to digress from carbon just to express this point. For example, I've got aluminium, right? So aluminium's outer electronic configuration is 3s2 and 3p1, which means it's 3px1, 3py1. Sorry, 3py would be 0 and 3pz would also be 0. Can anyone explain me if it's bonding, what would aluminium do to its electrons? Like,
S21 up.
okay, instead it's going to be 3s1, right? And
Yeah,
the 3 electrons will get distributed in different orbitals. The last one would still be empty. So that means when aluminum bonds, one atom, so one atom pulls electron in this direction, the other one pulls electron in this direction, and the last one. So all the electrons, they kind of get distributed. So you have to keep them in separate orbitals. So this is the maximum number of bonds that aluminum can form. The last one would be involved in dative bonding because that's empty, but we'll talk about dative bonding later on. At the moment, we're just talking about simple normal covalent bonds. Then you've got atoms that can vary the number of bonds, like phosphorus over here. Phosphorus outer electronic configuration is 3s2, and it's 3px1, 3py1, and 3pz1. So at the moment, how many electrons does phosphorus need? Like how many of its orbitals can bond with other atoms?
3.
3, because this one is already full. So this one doesn't need electrons, right? So only these 3. But in the third shell, if you remember electronic configuration, you've got an empty d orbital as well, 3dxy, which has 5 orbitals, 3dx, 3dyz, etc.
Sir, I can't hear you.
Can you hear me now? Can anyone hear me? Hello?
Yes, sir, I can
So
hear
yeah,
you.
I can hear you.
Can somebody type in the chat and
Yeah, I'll tell him so.
Yeah, now I can hear you.
Acha.
Okay.
Acha, so the third shell is really big. Like third shell, it's still not like there's another, like D has 5 orbitals, but all of them are empty. Like it's a completely empty D orbital. Now, phosphorus at the moment can make phosphorus at this moment can make 3 bonds. So उससे आगे बताओ कि what will happen if if it expands, if it distributes its electrons? Because the third shell is really big. It's got a lot of.
It can make 4.
What will it do with the 3s electron?
Well, it gives it to one of the
D. So now it can make how many bonds?
5.
5. So phosphorus can change the number of bonds it can form, right? And the same applies to atoms. So remember period 3. Group 2 cannot do that. Like if you have a group 2 element, the second shell can have just 8 electrons. That's it. So phosphorus has, and they do ask you a question on this. So remember, phosphorus has empty d orbitals in the third shell. And can expand its octet. expand its octet. But the other one, like if you talk about nitrogen, nitrogen can't do that. That's not possible for nitrogen, even though it's in the same group. Phosphorus can make 3 bonds. It can also make 5 bonds. So it can form PCl3, and it can also form PCl5 because of this. So there's going to be variable oxidation state. Like it can form 3 bonds. It can be +3. It can also form 5 bonds. It can be +5. Due to octet expansion. Now let's talk about nitrogen. Nitrogen wouldn't be able to do that because nitrogen has 7 electrons. So the outer shell is 2s2 and 2p3. So it's 2px1, 2py. Haji?
Is octet expansion the giving electrons to the...
This is octet expansion. Like you had, firstly, it was just trying to get 8 electrons, but the other orbitals are completely empty. So it can distribute electrons and it can have more than 8 electrons. Remember, the third shell can have a total of 18 electrons. Is that clear?
Yes.
So it can distribute its electrons and it can attract atoms and pull their electrons in this one, this one, this one. So it can bond with 5 things. Now, nitrogen will not be able to expand its octet because in the second shell, there's nothing after this. Like if you know electronic configuration, it's 1s2, 2s2, 2p6. So that's it. I mean, the second shell only has these 2. So there's no other orbital. The second shell is smaller. I mean, remember this, like the first shell is like really small. The first shell only has an s orbital with 2 electrons. So the second shell is slightly bigger. It has 8 electrons. The third shell has 18 electrons because the size is becoming bigger. So you can accommodate more electrons in that. So nitrogen cannot expand its octet. There's no empty orbital available. Is that clear?
Yes.
So just a minor point, and you get a lot of questions on this specifically. So remember period 3, sulfur can make many, many bonds. Sulfur can make 6 bonds. It can make 2, because remember sulfur has 6 electrons, right? But it can have a maximum of 18 electrons because it's a period 3 element. So sulfur has something like this as well. Lots of empty d orbitals. Same with chlorine. Chlorine can form many, many bonds. Chlorine can form 3 bonds. It can form 7 bonds. It can form a lot of bonds. Mainly because of the same reason. So let me just quickly quote. I'll just copy this. So chlorine kind of has just a second. So for the same reason, let's talk about Cl. Now Cl's original electronic configuration is 3s2 and 3p5. So it's 3px2, y2, and z1. Now, one way it bonds is right now it needs 1 electron. So Cl forms -1 ion, right? Because only one of these orbitals needs an electron. Is that clear? So that's Cl -1. But Cl can also form 3 bonds. What it can do is it can pull an electron from the 3py, keep 1 over there, and bring 1 in the empty orbital that's ahead of it. So now it can form how many bonds? It can form 1, 2, and 3 bonds. It can also form 5 bonds. Like it can pull an electron from here and expand it further into the next orbital. So now it forms 5 bonds. And it can form 7 bonds as well if it further expands and distributes all its 7 electrons, and each one bonding with a different atom. Is that clear?
Yes.
Yes.
But fluorine cannot do that. Group 2 cannot do that because group 2 only have these orbitals, that's it. So they can't go on distributing the electrons and maximizing bond formation. They can't do that. So hopefully that
Is there any element in
any element in period 3, yes.
any element in period 3 besides group 2 elements?
The period 2.
So this
You just
occurs
said group
only in
2.
period 3.
This will happen in period 3 and after that, because
Yeah.
then the shells are going to be bigger.
So even in period 4, 5.
Yeah, because those are going to be huge shells, right? So they can have as many electrons as possible. Is that clear? But you can't do that for like period
I
1.
see.
Yes.
So you can't do that for period 1 because period
And
1
period 2.
has only one shell and that's it. It only has only has one orbital in its first shell, which is S1. That's about it. So you can't expand it. There's nothing empty.
I see. Okay.
TK, is that clear?
Yes, sir. That's
Yes.
clear.
So octet expansion not possible. Period 2 can have maximum of 8 electrons. That's it. So remember the octet rule that you studied in O levels, that only applies up till the period 2 elements. That's it. But after that, period 3, it fails it. Then they can have as many electrons as possible. And normally, like chlorine forming 7 bonds is kind of difficult. Why do you think that's difficult? Like why is,
It takes a lot of,
huh?
it could take a lot of energy to shift the electrons.
Yeah, but the first thing is you would need 7 other atoms like ClF7. Does ClF7 exist? Just a second, let me just check. ClF7. I mean, I know Cl2O7 exists. I mean, you actually get this question. This question, that the first one that we get on Quora, that is actually an AS question. They're asking, in this case, ClF7 exists. There was another one, which was that ClF7 exists. It was a specific kind of question. Just a second. I mean, usually it's this one, the one that we did. Just one second. It's usually this one. They say that PCl5 exists, but NCl5 doesn't exist because there's no room for electrons. You can just have 3 electrons. That's about it. So only 3 Cls are going to bond with it. That's about it. But in that case, octet expansion is possible because of the empty d orbitals. Is that clear? So you get questions like this. So ClF7, anyways, that does exist. But coming back to the more important question that I was asking, and that was, why is it so hard for chlorine to actually make 7 bonds? So one of the reasons was that it requires a lot of energy because somebody has to pull those electrons. Like for carbon's octet expansion, there must be hydrogen coming in that's pulling those electrons, like ripping them apart. I mean, pulling one electron in this direction, one over there, one over there, one over there. So that obviously needs a force of attraction from somewhere, right? So imagine doing that for Cl's 7 electrons. Like there has to be 7 atoms that are trying to pull those electrons, which is kind of rare. I mean, it's not that easy to do. The other thing is making 7 bonds, spatially, there's a limitation due to space. Like imagine that you are the chlorine and there are 7 atoms trying to bond with you. So spatially, where would you keep those 7 atoms? There would be one on top of you, one on the right, one on the left. You'll run out of space. Is that clear as well?
Yes.
Yes.
So atoms usually don't make that many bonds. I mean, 6 is pretty hard because you run out of space. Like where do you keep that atom that's coming into bond? So even 6 is difficult. So anyways, just very quickly, let me explain Sp3 hybridization. What is going to happen? Sp3. So I'll just quickly explain. Sp3 is going to happen in this scenario when carbon makes 4 bonds and makes 4 sigma bonds. And quickly explaining, carbon has an electron in the S. Carbon has an electron. These are the X, Y, and Z axis. So I'm drawing the carbon atom. I'm drawing the 4 orbitals over here, the 2s1, 2px1, 2py1, 2pc1. So remember, there are 4 electrons at the moment are going to be located. There's going to be an electron. Let's say this is the x-axis. So there's going to be an electron on the 2px. And all of these orbitals are half-filled. So there's going to be an electron on the 2py. And there's going to be an electron in the 2pz. So imagine 4 hydrogen atoms coming in, and they're all trying to pull those. They're all trying to pull those electrons. Each one has 1 electron. Remember that. I mean, we just did that. Each one has 1 electron each. So S spherical. So this is Py, Px, Pz. And let's draw those 4 hydrogen atoms. There's a hydrogen atom coming in here. There's another hydrogen atom coming in over here. Hydrogen has a spherical orbital. And there's a hydrogen atom that's coming on top. So you've got your 4 hydrogen atoms, and they're going to try to pull electrons towards themselves, each one of them. And the top one as well. So all the 4 electrons, just like the image above, they're going to be pulled in different directions. So let's look at the blue orbital first. The electron over here is going to get pulled, and it will overlap with the hydrogen nucleus, which is trying to pull the electron. And the electron would stop going to the other side, right? So one of the p orbitals of carbon is going to be pulled or attracted towards the hydrogen atom, because the hydrogen nucleus is pulling that electron. Is this clear? This part clear, Mikhail, Hamza, Nima, is this clear?
Sir, can you repeat the
Yes.
last minute what you said? I lagged out.
Sunny, I said that carbon had this electronic configuration, right? It had 4 electrons. So I was showing this thing at the orbital level. It had 2s1, 2px1, 2py1, and 2pc1. So there's a spherical electron in the spherical orbital. There's an electron on the z-axis. There's an electron on the y-axis. There's an electron on the z-axis. Is that clear? The 4 electrons. Is this clear?
Yes.
And these 4 hydrogen atoms are trying to pull those electrons, right? I mean, this needs 1 electron, this needs, so they're all pulling those electrons towards themselves. So the px orbital, its electron is going to get pulled or attracted by the hydrogen over here. Is that clear? So the electron would stop.
Yeah, okay.
The electron would stop going to the other side, and the electron density would shift towards the left. So it's like the orbital is going to get pulled towards one side. The same thing would happen to this blue one, the electron density. The hydrogen nucleus over here will pull the electron, and the electron density would shift towards the hydrogen, and the electron would stop going to the other side. So the electron that was buzzing on the z-axis up and down everywhere, that has now got pulled towards the hydrogen at the bottom. And similarly, the same thing would happen over here. There's another hydrogen atom coming in with its nucleus, and it's going to pink one. So the pink electron over here is going to get pulled towards the hydrogen. The hydrogen is going to pull that electron, and the electron is going to shift towards that side, and it will stop going to the other side. Now, the last one is the spherical orbital. There's 1 electron, that's negative electron, that's somewhere in this area, buzzing in this area. And there's a hydrogen coming from the top, and the exact same thing, the red one, the red electron, the electron is going to get pulled towards this hydrogen atom over here. And the spherical orbital would change shape. Is that clear?
Yes.
Yeah.
So basically, it's simple. It's simple. Like if you had an isolated carbon atom, the electrons were all occupying their own space, px, py, pz, s. But now you've got these hydrogen atoms coming in, they're trying to pull them, and the electrons, they get pulled in different directions. So the idea is that when carbon bonds, carbon's orbital, they kind of look like this because they're getting stretched in different directions. So they kind of look something like this. One electron getting pulled over here, one electron getting pulled over here, one electron that's coming out of the page, and then there's one over here. So the electrons are getting pulled by 4 different atoms in a tetrahedral arrangement. Right? So the electrons are kind of, yes, Hamza.
So what would be the resulting orbital shape?
So the
Do you
resulting,
need to know that?
yeah, you need to know that. This is the resulting orbital shape. Now,
Okay.
and you have to give them new names now, because you can't call them an s orbital because there is no s orbital anymore. What happened to the s orbital? It got pulled towards that hydrogen atom at the top. So you have to give it a new name because the s orbital was a spherical orbital, which it no longer is. So you give them a new name and you start calling them an Sp3 hybrid orbital. And you actually, because all of them, they look exactly the same. So you start calling all of them Sp3 hybrid orbitals. So it's the same orbitals that you had, but now their shape has kind of changed. So these 4 orbitals now, when it's bonding, they would be known as Sp3 hybrid orbitals, and they would be identical. They would all look exactly the same. So Sp3 is just a name. Sp3, the word Sp3 just indicates that one of the S and 3 of the P's, they've all changed their shape. So instead of calling them 2S, 2Px, 2Py, 2Pz, you give them new names. Each one has 1 electron still. Basically, it's the same orbital, but the shape has kind of changed. So is the idea clear?
Yes.
So do you write Sp3 and then 1?
Yeah, I mean, it was.
Would you use?
I mean, you start calling 2s1 as Sp3 hybrid orbital. That's it.
Can you do something like 4 Sp3 and 1, like to show that you have 4 different?
Like, I didn't get what you're saying.
Like over here, you've written 4 Sp3 ones, right?
Yeah, I mean, because this is an Sp3 orbital, this is also an Sp3, this is an Sp3. This is, I mean, you give them all the same name because they all look exactly the same.
Oh, right.
I mean, before that, they were all different, right? You had 2s, you had a 2px, you had a 2py, you had a 2pz. But once the bonding started happening, the electrons got pulled in 4 different directions. And the orbitals now kind of look completely different. So you start giving them a new name. You just give them a new name. That's Sp3 hybrid orbital. Is that clear?
Yeah, so it's called Sp3 because 1s and 3p orbitals, they bond together. That's why, right?
They mix together. Or simply just ignore. Just ignore. Don't get confused with the name. That's just a name. I mean, it has no special significance. It's just a name that they gave to these orbitals.
Oh, okay.
Okay. So just remember, when does carbon form Sp3 hybridized orbitals? When it's making 4 single bonds or 4 sigma bonds, and it's got a tetrahedral shape, and the angles are going to be 109.5 degrees. So tetrahedral is, we're running out of time. You can just Google tetrahedral. We'll continue tomorrow. We'll do the other hybridization of carbons. So that's the first one. Is this clear?
Yes, sir.
Yes, sir. All right.
So let's continue tomorrow then.
Okay, sir. Allah Hafiz.
Hafiz.